Hi, today we're going to be talking about estimation as an approximation method, okay? We're going to deal with three things. First, we're going to talk a little bit about what is the data analysis process in general. Second, we're going to concentrate on estimation, and to do that, we will do some simulations. So I will show you how different techniques approximate the data, and then I will talk a little bit about how can we choose if we don't know what the model is. So this exercise is kind of to introduce all the topics that we will have through the semester, but also to highlight a little bit of the complexity of the problems that we have. So first, what is the data analysis process in general? So the way I think about it, it has three components. One component that is related to the data collection. This is in general is when we have problems in the data collection, we think about the integrity and the reliability of the data. The second one, which is the data analysis, that is a typical process where we just do a design, then we do an estimation, then we analyze, then we redesign. So it's an iterative process. And here we will have problems of specification that we will discuss a lot through the semester. And then at the end, we have problems with the data dissemination. These are issues about privacy. For example, these are things about the use of the data and how we use the data. So in general, we will pay attention to all three of them. Now, the typical course on data analytics actually doesn't have the emphasis like this. Actually, it will look more or less like this, where people spend almost all the time on the fun part, which is you design, you estimate, you analyze, and then you redesign and so on. So you spend all your life in this circle. However, and in fact, very rarely we pay attention to the data collection or the dissemination. So no wonder why there are so many ethical issues in the use of the data. We are not, my experience is that actually this is not how the world looks like. Actually, my experience is that the world actually looks like this, where there's a massive problem on the data collection. And in fact, the better you collect the data, the easier is the estimation part. And second, the ethical aspects of the data dissemination are extremely, extremely important, and we very rarely pay attention. Our course is going to devote a lot of time to the estimation, so it's not going to be an exception that we will devote a long time of the semester through how to do the proper estimation. But we will not forget the issues of data collection and data dissemination at all, okay? So let's talk a little bit about estimation. And in fact, estimation is formally is a rule by which we try to determine what the function is in the data. So we have two variables, let's say x and y. We would like to know how they are related to each other. And what we're going to do is to use the data to approximate that relationship. The purpose of that estimation is very important to determine the weaknesses of that estimation. So we're going to devote a little bit of time to what is the purpose of any form of estimation. The second one is that given the purpose, then how can we evaluate how good that estimation was? So we want to evaluate the fit. And lastly, again, understanding what the purpose and how we're going to evaluate the fit, what doubts do we have? So what are the problems that regressions might have? And so these three things are important, and they're very intertwined. If you're going to use the data as to inform other data collection methods, so that's a purpose, then the problems that appear there are of different nature that if you want to do a forecast or if you want to understand the behavior. So the purpose, the evaluation of the fit, and the problems that arise in those estimations all of them are very intertwined. Let me just first show you a simulation. And we are going to use a lot of simulations in this course. And the reason is that we know how we created the data. So there's no doubt about what function we are imposing. So we know what the relationship is. And the question is, can we recover that from the data? And so these are the ways we're going to understand a little bit of the limitations of all the techniques that exist. So I want to start by showing you a simulation because we will do many of those, but also to show you that how difficult this is, even though the data I'm going to show you, the only problem that it has noise. That's it, okay? So let me just show you the simulation, okay? We're going to use many different techniques. We're going to estimate linear regressions, also OLS. We're going to estimate nonlinear regressions. We're going to estimate decision trees, neural networks, etc. So I'm going to show you a battery of different tools, how we're going to do the estimation. We're going to try to understand which one is better. And that, again, the purpose here matters. But at all times, we will know what the true model is because we created data. So let me just describe what the true model is. In blue, we're going to have some constant, and this is just we're not going to pay a lot of attention to that constant, but there's some constant. And we're going to have an x and a y that is a concave function. So we have a quadratic function where the alpha coefficient is going to be 3 and the beta coefficient is going to be minus 0.5. So that function looks like this. Okay? And we have noise. That's it. And in fact, this noise is going to be a very particular form. It's going to be normal, and the covariance between x and the noise is exactly 0. Expected value, so the covariance is exactly 0. So it is actually the perfect assumption to run regressions. We want the errors to be uncorrelated with the x's, and you will see that we will repeat that all over the place. It's called exogeneity, but we will come back to this point. But this regression, the only thing that it has noise. I'm going to create 1,000 draws. This is the size of the noise. This is the standard deviation. So this is how the data looks like. And in fact, the x is not equally distributed from 0 to 6. It just has more in the middle. That is just, a feature of the simulation that I did. And this is the y. Now, if you look at this, clearly this looks very quadratic. And the question is, well, can we recover that? We're going to estimate different models. And every time we're going to estimate a model, we're going to be imposing constraints. So when we tell the computer, I want to estimate through OLS, is that we are imposing a linear function there. And we're going to say, we're going to estimate that linear, and we're going to have that line, and we're going to know what that alpha will be. Of course, we know that that model is wrong, but we will see what happens when we run this regression. The second aspect will be, we're going to estimate a quadratic. We know that that should be the model, so this one hopefully is very good. And in fact, we will try to understand what good means. But we will also do an estimation that is called a series estimator, where we put different x's. In fact, we're going to do an 8th degree, so it's going to be a polynomial from x to the 8. That's a very flexible function because it's going to fit different curves. We're going to do a decision tree and a random forest. A random forest is a more complex way to estimate decision trees, and we will discuss that in class. And we will do a neural network and deep learning. And again, these are very famous ways of estimation. Deep learning right now is receiving a huge amount of attention in the literature and in applied work. Okay, in fact, I will show you in a second how they look, and we will learn about these techniques throughout the semester. I just want to show you. I'm going to impose the same data. I want to look how the different techniques are able to approximate the data that we are observing. Okay. So if I estimate OLS, this is what happens to that data. So it estimates a line, and it crosses through the data. And as you can tell, this doesn't look very good. I mean, there are parts of the data where the errors tend to be very large, in this case, very large and negative. And these are on the extremes. And we can see that, it doesn't look that good. But we would like to have a sense of, how bad this regression is, and in a second will be. But when you tell the computer, I want a linear regression, the computer is going to say, well, I'm going to assume that it's linear, so let me try to find what is the best linear that approximates the data. Now, if we do the quadratic one, it looks like this. And now, it looks better. It's closer to the data, no? So, and by the way, we know that this should be the correct one, so it's not surprising that it performs just to the eye test better. I'm going to be more formal about these statements in a second. I will do that. When I put the 8th degree polynomial, it's interesting that it looks very similar. They are not identical to the quadratic one. You will see tiny differences in a second, but it just has the same shape. So we expect that. And so how do we evaluate this? Well, there are two parts of the evaluation of that. We tend to look at significance and R-squares. And in fact, you have learned some of that in previous courses. This is how the regression looks like when we have only one x, so it's linear, it's actually negative, and it's very statistically significant. The R-square is tiny, it's about 5%. When we put quadratic, notice that the coefficients are kind of what the true ones. No, this is very close to 3, and this one is very close to minus 0.5. So that's really cool. And by the way, you can see that the R-square increases highly. So if we are evaluating these regressions in terms of R-square, we would say that the quadratic is better than the linear, and in fact, not surprisingly, it is. Our eyes were telling us that this has to be the case. Now, when you look to go to a series estimator, look what happens. Actually, the R-square continues to improve. And in fact, the adjusted R-square that is punishing for the number of regressors is also improving. So according to this, if you were choosing R-square, you will choose the series estimator. But notice that here, not a single coefficient is statistically significant. In fact, the standard errors of the coefficients are in parentheses, and you can see the standard errors are incredibly large. The coefficients are about 0.6 and the standard deviation is 11. So everything is 0, but in the aggregate, they explain 36%. That's surprising. That is called multicollinearity. And we will discuss a little bit of that on more technicalities aspects, but we will come back to this. It's actually something that happens when you put regressors that are very correlated with each other. And in fact, x and x cubed are incredibly correlated. That's what happens. So one is picking up the other, and therefore it just makes the regression knows that there's something here that is important, but the computer cannot pick what it is. Notice that the coefficients are far from the true ones. Now, let's estimate a decision tree. A decision tree is a regression where you specify very simple rules. And in the estimation, this is one decision tree that was estimated. One of the problems that decision trees have is that they are not unique. If you run the regression again, you will get a different number. So in this decision tree, it is asking, well, if x is bigger than 4.6, okay? If it's yes, go to the left. And then if it's bigger than 0.5, then assign the number of 1.7. If it's less than 0.5, but bigger than 4.6, assign the number 3. Now, if you go to the right, then they ask the question is if it's smaller or bigger than 1.3, bigger or smaller than 3.9, 2.5. So you see, depending on which range the x is, what it's telling you at the end is what number you will assign. You will assign in either the number of 3, 3.8, 0.86, etc. So I hope that you see that what the decision tree is doing is takes a range of the x and assigns a number. So it looks like a step function. And in fact, technically, a decision tree is an approximation where we take step functions to approximate the data. Okay? Therefore, we choose thresholds and then we choose levels. And therefore, we produce a tree like this one. And in fact, if you do the predicted value, the blue line, this is how it looks like. So the first thing is interesting because this doesn't look that bad comparison to the quadratic one. So if you didn't know if the data was created by a quadratic function or some threshold decision in the consumers, it's not clear how you will pick between the two. Random forest is an extremely good technique for predictability. I force random forest here to be incredibly good at picking and matching the data. So I pick about 500 trees, so that's too many probable. But I just wanted to take the extreme so you see big differences. When you do the predicted value from the random forest, this is how it looks like. What it's doing is predicting all the noise, and they're really good at predicting noise. So here is predicting noise. I want you to see how good it is to the extremes. It's actually fitting the data on the extremes almost perfectly. I mean, much better than the quadratic one, for sure. But it's just picking all the numbers in the middle. So it's just, you can see how noisy it is, that prediction. So a neural network, for example, what it does is takes the value of x and then uses functions that are not necessarily continuous, but there are functions that are called the activation functions. And all the activation functions tend to look at something like this, okay, from 0 to 1. And those activation functions are of different forms. There's one that is called sigmoid, hyperbolic tangent, the inverse of the trigonometric tangent, etc. So there are many functions that people use. And the reason why they look like that is because neurons have activation functions that look very similar to that. So the neurons are 0 or 1, and they tend to actually have that shape. So what we're doing now is approximating the data by collection of little s's. So for example, we look something like this. That's it. So the quadratic might look like that, and then the data points are just distributed along those points. So this is what the regression is trying to do. It's approximated by that. So here I allowed 10 of these little wiggles, and this is the prediction. And here I want you to see also that they are very good at predicting these extreme realizations. They tend to try to fit those extreme realizations. And look at the middle, you will see that it's not monotonic, goes down and up, okay? So not a single concavity. And it's actually trying to approximate not only the underlying data, but also part of the noise. But that's what the neural network is doing. Deep learning is a neural network, but that has 2 layers of those sigmoids. So this is a layer of 10 and then a layer of 5, and you choose these parameters. So here is a wiggle that enters into other wiggle, and then they are all related. And the numbers on the lines, I forgot to say that, but the numbers on the lines are the weights. So this is the X entering here with that weight, and you choose a threshold, and that tells you where the little s's are. So this it's a very flexible functional form. It's very complex. And then it's trying to fit the y's, okay? You start with an x, and you try to fit the y, and it's just trying to choose the combination of those little s's to try to match the data as close as possible, and this is how it looks like. And again, notice that it's very good at hitting the extremes of that realization. So how can we tell which one should we choose? So imagine that I show you this data and you didn't know. So, and if you want to estimate a neural network, well, it will look very good. So, first, let me talk a little bit about the issues with estimation of what will be the purpose. So, again, remember, what we're doing is we're trying to approximate the data or the function that relates the data using the data itself. So, we're trying to calculate that function approximating from the data points. So, the question is how we're going to use that. Well, it's different if you want, for example, to use this data to inform other statistical processes. So, for example, if I'm going to use this exercise today to determine what is the type of questions that I have to ask later, well, what makes a good regression, what makes a statistical procedure good or bad, well, depends on how you're going to use it, okay? So, for example, you can use a procedure to determine that you need to collect more data. For example, that will be one. Now, if you want to do forecasting, for example, this will be the second one. So I want to just look at, at the future. Well, now I want to use different techniques to determine if what I'm doing is good or bad. For example, if I want to understand why something is happening, well, that is something about causality. Well, I need to do different things to understand when that is good or bad. And when I want to measure, which is what is happening today, those are different requirements. So you can use any statistical procedure to inform other statistical procedures, to forecast, to understand causality, or to measure, to understand what is happening. Depending on this, there are different ways to evaluate if you're doing a good job or a bad job. And there are different ways and different techniques and different problems that will arise. So the evaluation of the fit, you probably have heard about R-square, which is what is called the within sample explanatory power. So this is more or less to try to understand, it's on the measurement, tends to say, well, am I explaining the data? Am I explaining today? The out sample is for the forecasting. I want to predict something that has not happened yet or in a data that doesn't happen. So extrapolation is very important. And there are techniques that engineers use. It's called cross-validation, which is extremely powerful in that sense. When we want to understand causality, it's about significance and a specification test, etc. So depending on how we're going to use the data, there are different aspects that we have to evaluate whether or not we're doing a good job or not. Finally, there are different problems that we will face. So we will devote a lot of time to specification problems. These are omitted variables, errors in variables, etc. So we will devote a lot of time to those issues to understand them. We're going to devote a lot of time to stability. So is the model of yesterday the same as the model of today, or is the model for one group can be used for another group? So for example, if you were estimating something among men, I don't know, promotions, well, I don't think that you can use that model for women, okay? It's not stable. So discrimination will show in the parameters and the coefficients of that model. So stability is kind of an important property. And that leads to the generalization. Can you generalize something from one group to another? How can you extrapolate from one time to the other? There are issues with the data collections, and we will do exercises for that. And there are many, many issues with the ethical aspects of the data dissemination. So again, depends on how you're going to use the data. If you're going to use the statistics to determine how to do another statistical procedure, you are truly not disseminating anything. So therefore, in that sense, the data dissemination issues disappear. But if you're going to use this to forecast and then do investments related to that, well, the dissemination is kind of important. So let me just tell you a little bit. We have techniques that are to detect patterns on the data. They tend to be used, for example, to inform other statistical processes. And in fact, in typical, what we want to know are those patterns helping us or not inform the next procedures. There are very few problems in that world, but it's about detecting patterns. In the forecasting, what we want to know is stability remains the most important issue. Can you use today for tomorrow? And what I want to answer here is what will happen. So it's what will happen. There are huge issues about the dissemination of the data with forecasting. Discrimination is one of them, and we will actually look at those, okay? When you want to understand causality, which is more or less what we economists tend to do, we want to understand the phenomena that is happening. It's not good for us to predict something. We want to understand the why you are predicting it. So significance is very important. And here, specification errors are the problem that appears the most. Also, there are extrapolation issues. But again, you can understand the causality in one group of the data, but not in the others. Finally, a measurement to me is the most difficult one because it's a combination of the why and the forecasting. So it is about what is happening. So I want to understand the causality, but also want to understand fit. So it's about how good you are. So let me just show you what we did with the data, and let me pick two different objectives. I'm going to pick the objective of measurement and then the forecasting. Causality here is a non-issue because we know that X is causing Y, so there's nothing we can actually do here for that. But I want to look at two issues, measurement and forecasting. So if we had to use those, what will be the criteria? So for example, for measurement, am I capturing reality here? The R square is a very good one. So we know X is exogenous. Are we doing a good job by capturing the data? Are we explaining the why properly? That's what the R square will be. So if I list all the techniques that we use, this is how they look like. So the quadratic, by the way, the linear performs horribly, okay? By the way, our eyes were telling us that that's a bad one. And by the way, random forest also performs badly. But this is because I'm kind of making random forest to be, to try to feed the noise, okay? So it's just horrible in that sense. So I'm forcing it to fix the noise, just wanted to show you the case that you can make those mistakes. But quadratic is good. It's a 35% R square, as we saw, the same number as we saw before. But notice, decision tree is just barely worse. And in fact, neural networks are better. So if you were to choose, and by the way, the Sears estimator is also better. So if we were to choose only based on the explanatory power, we will not be quadratic, even though we know that that is exactly our model. And there's nothing wrong with the regression except noise. Now, you said, well, but maybe, this is because it's within sample. And in fact, because neural networks are fitting the extreme observations, where that's where the OLS and the quadratic are making the biggest mistakes, that's why they're getting better scores. That's actually the reason why they're getting better scores. So let's for example, look at another criteria, which is, imagine that instead of answering that, we want to understand, well, how good are you at forecasting a data that doesn't exist? So the out of sample prediction. So this is the original data. I know it's small, but yes, it's exactly original data that I just showed you. And these are new data points that I created. So new 500 observations, created them exactly the same. The alpha continues to be minus 0.5 and the beta continues to be 3. I just created new x's and I computed new realizations. So the only difference between the two samples are the residuals. So the epsilons are the different aspect here. They are different epsilons. Let's look at now I do the estimation on the left-hand side, which is my training data, okay? Or my in-sample, and I evaluate the R-square, for example, on my testing data, or what is called the out-of-sample. Okay? So let's see how this performs. First, OLS is linear is so bad that actually give you a negative number. Okay, so you explain a negative amount of the data. The quadratic is doing relatively well, but notice we have many that are as good as quadratic. So even the out of sample, you will not pick quadratic necessarily. Isn't that interesting? So we're going to come back to these issues along the course. But I think that having the intuition that estimation is an approximation make us realize that we are a very important component of that estimation. If we ask the computer to try to fit a quadratic equation, it's going to pick the best quadratic equation that approximates the data. And if we change that and we put a neural network, then we're actually forcing that model into the data. So it is not the case that the data always speaks by itself only. In fact, here, if you estimate all the models and you allow the data to pick which model to predict, by the way, if I put the random forest to be more, not as punishable as I did here, actually the random forest, I can get that to get to 0.30 on the out of sample. So it will be better. You will pick the wrong model, and we know it's a wrong model. And the only thing that this model has wrong is that it has noise. That is not perfect. That the relationship between x and y has a component that is not related to x and that is random across the individuals. So that is a very important aspect of what we're going to discuss, because we always are trying to understand what the true data is telling us, but we have to understand that by us imposing the models, we are making mistakes. Now the computer doesn't know that we're making those mistakes, so we're going to try to find the best approximation given the mistake that we're making. By the way, that's actually the case of linear. We know we're making a massive mistake there, but the computer doesn't know. So it tries to find the best linear for that particular data set, gets the best approximation, and it just happens to be that it's a disaster. Okay? See you in the next video.